This is Tuesday, May 18th, 2021, Chemistry CP. In a previous episode, we did a calorimetry problem just for fun, kind of a review problem. And there's been a student request to review a bit more exactly how to do calorimetry problems. So here we go. Once upon a time, I distributed a reference sheet that included some formulas on it related to calorimetry. This first one says the heat energy Q of a temperature change, or related to a temperature change, is the product of the mass of the substance times the specific heat of that substance times the change in temperature for that substance. Skip this, skip that, skip this, skip that, skip this and that. If the substance melts or freezes, then the heat energy Q for that phase change is the product of the mass of that substance times the heat of fusion for that substance. And if that substance should boil or vaporize or condense, so vaporize or condense, then we use this formula, which says the heat energy is the product of the mass of the substance times its heat of vaporization. And then a reminder on how to convert between Kelvin and degrees C, between Fahrenheit and degrees C, and between calories and joules. In this table, it's somewhat incomplete, but for some, for where there is information, MP is the melting point, BP is the boiling point, C is the specific heat in solid, liquid, or gas, heat of fusion, heat of vaporization. I did not update this table. In the current school year, we've been working in units of joules per gram per degree C. But this table is listed in joules per kilogram per Kelvin. So the conversion is, since there are 1,000 grams in 1 kilogram, and since a change of 1 degree C is equivalent to a change of 1 Kelvin, we should divide the numbers on this table by 1,000 to get them into the units that we're using this school year. Okay, so if we have, for example, for water, the specific heat of water on this table says 4,180 joules per kilogram per Kelvin. That is equivalent to 4.18 joules per gram per degree Celsius. Because a change of 1 Kelvin is a change of 1 degree Celsius. And there are 1,000 grams in a kilogram. So move the decimal point 3 places, and now you have it in the units that we've been using during the current school year. You can ignore this comment. It's just a little note to myself about what I really want to talk about today, and the punchline of what I was reading in today's headlines. The only constant in nature is change. Yeah, very profound statement. What? Nah, sorry, that's not, no. All right, so we're going to just practice doing some calorimetry review, hoping that this gives you greater confidence that you can do the actual homework calculation correctly. So I'm going to just make up a few problems. I have a beaker. Into this beaker, I put some solid object. I'll draw as cube-shaped. I've got some liquid. Let's presume it's water. Let's say that the mass of the water is 132 grams, that its initial temperature is 20.1 degrees Celsius, that I add a hot substance to this water. Oh man, I could add a cold substance. That'll throw you guys off. Oh, we'll make it a hot substance that I'm adding to this water. And let's say for the hot stuff, its initial temperature is 216 degrees Celsius, that its mass is 42 grams. And after I add this hot substance to this cold water, they reach a final equilibrium temperature of 32 degrees. But on a Celsius scale, that does not mean the freezing point of water. It would on the Fahrenheit scale. All right. And my challenge question for you is, out of the table of possible substances, just this list, which substance comes closest to being the substance used in this made up problem? Now, I just did this off the top of my head, so it's not going to be exactly matching anything. But out of the range of numbers and the limited choices, we can narrow it down and say, oh, okay, it's closest to this or that. No doubt you students remember how to do this problem. The heat lost by the hot stuff cooling down is equal to the heat gained by the cold stuff warming up. And whichever side you're on, the change in heat energy is the product of mass times the specific heat of the substance times the change in temperature for that substance. For the cold water warming up, the mass is 132 grams. The specific heat of liquid water, on this table it says 4,180. So now we know we need to express that as 4.18 joules per gram per degree C. The change in temperature for the water is 32 degrees C, the final temperature, minus 20.1 degrees C, the initial temperature. And I'm too lazy to even do that one in my head. 11.9 degrees C. Okay, so meanwhile, for the hot stuff, don't know what it is, we can say its mass was 42 grams. The specific heat of it is unknown because we don't know what stuff this is. And the change in temperature for the hot stuff is different from the change in temperature for the cold stuff. They start at different temperatures, but they both end at the same final temperature. For the hot stuff, I'm going to write it backwards. I'm going to write the initial temperature, 216 degrees C, minus the final temperature, 32 degrees C. And by the way, that is backwards from how you're supposed to do it. You should always do it final minus initial. Always final minus initial. I'm cheating. I'm choosing to make this a positive number instead of the negative number it really is, so that I can set one positive number equal to another positive number. Yikes. Well, I'm too lazy to do this in my head. 216 minus 32 is 184 degrees Celsius. Okay, next step, pretty easy. How much heat energy did the cold water gain? Calculate, please. How much heat energy did the cold water gain? All right, so my students and I calculated, I agree with my students. They calculated 6,500, and to 3 sig figs, you would round this thing up to 70 joules. That's how much heat energy the cold water gained from the hot metal cooling down. So we can set this equal to the heat energy lost by the hot metal cooling down. And that means it's the product of the mass, 42 grams, times the unknown specific heat, times the change in temperature, which I'm expressing as a positive number, as 184 degrees C. This becomes a Math 1 problem where there's only one unknown, and that is the specific heat of the unknown hot stuff. Calculate, please, what is the specific heat of the hot stuff? Okay, my students calculated. The specific heat works out to be 0.8. So really the calculator says 0.84963043348. But to 3 sig figs, you should round that to 0.850. And the students correctly knew that the units are joules per gram per degree Celsius. Okay, so based on that result, we go to the table. Now, if we went on the internet, there would be a huge table, multiple pages long of values. But I'm going to restrict us to only what we see on the table in front of us. And so we're looking for something which in our current year units is 0.850 joules per gram per degree Celsius. But on this old table, that would be 850 joules per kilogram per Kelvin. So we're looking for a number closest to 850. Well, I hope it's obvious enough. No, 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 no. Yes. So the closest choice is aluminum. The nearest alternate would have been iron, and this is way closer to aluminum than it is to iron. So we're going to stick with making this bold claim that the substance is probably aluminum. Okay, ta-da! It isn't exact because we made these numbers up and I didn't take the time to make them exact. Let's do another practice calculation because you students could use the practice. We actually ended up with a horrible example last period. So let me remind you what happens if we do have a horrible situation. Anytime that we have heat energy added or removed from a substance, we must always follow the heating curve, which means it begins as a solid. And we can heat up that solid, but only until it reaches its melting point. Then we would have to melt the substance, turning it into a liquid. After it's a liquid, then we can heat it, and it might have a different slope. pretty much always does, until it reaches its boiling point. Once it's at its boiling point, it undergoes a phase change again, turning it into a gas. And then finally, once it's a gas, then you can heat it even further. So here is the little stick figure sketch reminding you of the heating curve. So as you add heat to the right, the temperature goes up on the left, and we begin with solid, then it becomes a liquid, then it becomes a gas. Going to the right, we would call this melting. Going to the left, we would call it freezing. Going to the right, we would call this vaporization. Going to the left, we would call this condensation. And there is a term for going directly from solid to gas, but we're not dealing with those substances these days. Let's take another beaker of water and in this beaker of water, I'm going to put in an iron cube. The water is a mass of 260 grams. Its initial temperature is 17.8 degrees Celsius. It's liquid water. For the iron, of course, you recognize the chemical symbol for iron, Fe. Its mass is 50 grams. Its initial temperature is blazingly hot, making it how hot? That's not very hot. Oh my goodness. Well, for starters, the melting point of iron is 1,538 degrees. So in theory, we could go up all the way to that number. But let's make it 400. That's crazy. Why would I make this so horrible? Let's make this 240 degrees Celsius. Okay, so the initial temperature of the iron is 240 degrees Celsius. If I really started at 400 degrees, then I might be getting into the possibility of vaporizing all of the water. And I didn't want to make it quite that complicated. That's what happened last period. I did not record it. And so they're saying, oh, Mr. Turek, you went easy on this class. That's true. All right. And so now my question for you is what is the final temperature in this situation? For the cold water, of course, Q equals mc delta T. And for the hot iron, Q equals mc delta T. It's not the same delta T. This is for the cold stuff warming up to the final temperature. This is for the hot stuff cooling down to the final temperature. I can tell you already, the hot stuff is going to have a much larger delta T than the cold stuff in this situation for two main reasons. There's a lot more water than there is iron, and the specific heat of water is greater than the specific heat of iron. So this is going to change temperature a lot compared to that, less. How do we find the final temperature? we have to kind of expand the delta T so that we have one nice, huge math 1 equation with one unknown in it. So for the water, of course, its mass is 260 grams. The specific heat of liquid water is 4.18. And sometimes I'll say 4, sometimes I'll say 6. I really don't like 0, but we'll leave it as 4.18 joules per gram per degree C. The change in temperature is a mystery, but we can express it as the final temperature T sub F, whatever that unknown value is, minus the initial temperature of the water, 17.8 degrees C. Now you're saying, I've just traded one unknown for another. Yes, I have. This one I cannot solve for. That one I can by working over here with the hot substance. The mass of the hot substance is 50 grams. The specific heat of solid iron, well, on this table, it says the specific heat of solid iron. Good thing we're not dealing with liquid or gas because it's unknown on this table, is 450 joules per kilogram per Kelvin. Dividing that by 1,000, I'm going to write down 0.450 joules per gram per degree Celsius. And the change in temperature for the hot stuff cooling down, I am going to write it backwards again. So I'm going to write it as initial temperature, 240 degrees C, minus the final temperature, which we don't know. The final temperature for the hot stuff cooling down is equal to the final temperature for the cold stuff warming up. So I can set these two equations equal to each other. And that will lead to one big equation with just one unknown. (260 grams) times 4.18 joules per gram per degree C times the final, well, in parentheses I'll do it, times the final temperature minus 17.8 degrees C, close parentheses, is now going to be set equal to 50 grams times 0.450 joules per gram per degree Celsius times, open parentheses, 240 degrees C minus the final temperature, close parentheses. You students took math. You love math. You probably wish you were in math class right now. You're probably thinking this is like a math class right now. I have one equation and one unknown. I'm going to get rid of the parentheses by using the distributive property of multiplication. So 260 times 4.18 is 1087 times the final temperature minus 19,345 joules. All right, we finished our 3-minute break. I've used the distributive property to go A times B times C minus A times B times D. And so here's ABC, here's ABD. Set it equal to E times F times G. Oh man, 50 times 0.45 times 240. So I get 5,400 joules minus 22.5 times the final temperature. Out of all this, I now have one equation and one unknown. It shows up in two places. So combine like terms. I would add 19,345 joules to both sides of the equation. That gives me 24,700. Oh, I know I should just round it. 50 joules. Even that is 4 sig figs already. Adding 22.5 times the final temperature to both sides, 1087 plus 22.5 is 1,100, let's just call it 10 times the final temperature. Dividing both sides by 1,110, 24750 divided by 1110, enter. The final temperature in this example is 22.3 degrees Celsius in this example. I'm hoping that this is enough review that you students can go on from here and work out the solution to last Friday's exercise, which was I have a beaker of water, I put 20 grams of hot copper into it, I measure the initial temperature and mass of the water, the final temperature of the water, I know the mass of the copper, I know it's copper, I know it's water. The only thing unknown is the initial temperature of the copper, and that is the one unknown that you solve for. Ta-da!